Hey guys, so today we're going to be talking about the graphs of circular functions and trig identities, but let's just start out with reviewing what we know about graphs of circular functions. So, y equals sine of x, this is our equation, and remember that the function of sine is typically going to look like this in an equation. And let's go over what we already know. We remember that A represents the amplitude, which is the height of the graph, and we can also remember that B is going to be represented in the equation to find the period. That's the equation 2 pi over B. And we know that C is going to equal the phase shift of the graph, how much it's shifting horizontally. And we know that D is the vertical shift up or down. So let's go ahead and work on a problem. Y equals 3 sine of 3x. So this is our first example problem. So we can see here that automatically we know that 3 is the amplitude. And we can see that 3 represents B. So we're going to take our equation to find the period. We're going to substitute this 3 for B as we see here. So 2 pi over 3 equals 2 pi over B. We're going to solve for 2 pi over 3 is the period. Okay, so now we're working with cosine, and cosine pretty much has similar properties to sine. Cosine's function is typically going to be represented like this. Like so. Y equals the cosine of x plus pi over 4. Then we know that the amplitude is non-existent, so the amplitude is technically going to be 1. B is also going to equal 1. And when it's in this form, we know that C, the phase shift, equals pi over 4. So we're just identifying different functions. We know that a cosine graph typically is going to look like this. While a sine graph will typically look like this. Like so. So those are the differences. Sine is usually going to cross the origin, and cosine will usually go over or under. Okay, so now we're moving on to focus on trigonometric identities. So the first thing we're going to go over here is the reciprocal identities, which we used way at the beginning of trig, and it helped us to memorize our sine, cosine, secant, cotangent, cosecant functions. So right here, cotangent of theta is equal to 1 over the tangent of theta, just like the tangent of theta is equal to 1 over the cotangent of theta, vice versa. Then we have the cosecant of theta is equal to 1 over the sine of theta. Then we have the secant of theta is equal to 1 over the cosine of theta. Now we're going to go over quotient identities, and I will warn you guys, we are going to go over a bunch of different identities, so brace yourself. So tangent of theta is going to be equivalent to the sine of theta over the cosine of theta. Okay, so the cotangent of theta equals the cosine of theta over the sine of theta. And obviously these equations aren't set. Like for instance, over here you can multiply cosine out on this side and then multiply the cosine of theta by tangent of theta. And then if you divide tangent of theta, you'll get that the cosine of theta is equal to the sine of theta. So let me just write that out here as an example with pencil. So if I multiply cosine of theta here, that cancels out. Then I'll multiply tangent times the cosine of theta. Then I decide to divide this new function by tangent of theta, which means I have to divide this side by tangent of theta. Then ultimately it's just going to be equal to the cosine of theta equaling the sine of theta over the tangent of theta. So yeah, you can mix this up for all the identities. Now we're going over Pythagorean identities. So sine squared of theta, or sine of theta squared plus the cosine of theta squared equals 1. And then here, writing the tangent of theta squared plus 1 equals secant of theta squared. And then our last one here is 1 plus the cotangent of theta squared equals the cosecant of theta. So as you see here, things get a little different because it's not our usual sine and cosecant and cosine and secant, so that might get a bit confusing, but these are Pythagorean identities. Now we're doing even odd identities, and here you can see I've already written it out, and I've already distinguished which ones have the odd identities and which ones are even. So you can see the sine of negative theta equals the negative sine of theta. Cosine of negative theta equals the cosine of theta. So as you can see here, this is producing negative and this is producing positive. So as you can see here, the even ones are the cosine of negative theta and the secant of negative theta, and those are both functions that are producing values that don't include the negative number. So that is definitely something you can also use to distinguish it from the odds and the evens. One thing to remember is that theta can represent anything from an angle in degrees to a real number or a variable. And this is something you really want to take into consideration when working with trigonometric identities. Now I'm going to demonstrate an example problem that incorporates the trigonometric identities. So here our problem is if tan theta equals negative 5/3 and theta is in quadrant 2, find each function value. So our first part of the question asks for the secant of theta. So now we're going to have to look for an identity problem that allows us to find the secant of theta using tan. And that's going to take us back to our Pythagorean identities. Remember what I mentioned earlier. So our Pythagorean identity involving tangent and secant is going to be tangent squared of theta plus 1 equals secant squared theta. So we know here that since our our problem tells us that tangent of theta equals negative 5/3. We can put negative 5/3 here in place of tangent. And remember, we're replacing negative 5/3 with tangent itself, not with theta. Okay, because we know that tangent of theta equals negative 5/3. But we keep this square because negative 5/3 only represents tangent, not theta. Do not make that mistake. The theta, okay, so when you simplify that, negative 5 squared is going to be 25 over 3 is going to be 9. And whenever we add the 1, we're going to have to simplify it to have a denominator of 9. So it's going to be plus 9 over 9, which is going to give us 34 over 9 equals secant theta squared. So that's going to give us, I'll write it over here, secant of theta is going to be equal to, and since we know that it's in quadrant 2, secant is going to be negative. So if we find the square root of secant here, it's going to equal the square root of that. So our problem is ultimately going to be the square root of 34 over 9. And that is going to be the value of secant if the tangent of theta is negative 5/3 in quadrant 2. Okay, so the first thing we're going to do is we're going to multiply out cosine and move it to this side. So that's going to give us the cosine of theta times the tangent of theta is equivalent to the sine of theta. Now we're going to make this problem a bit easier for us using reciprocal identities. So we know that cosine of theta is equal to what? Reciprocal identity. That's right, 1 over the secant of theta. And we're going to multiply that by tangent of theta equals sine of theta. Now, thanks to our first part of the problem, we know that the secant of theta is going to be equal to, square root of 34 over 9. Now we're just going to simplify that because we don't want to have a square root as a denominator. We can't have that. We'll have to rationalize it. So we're going to simplify that, and that's going to give us, oh yeah, it was negative. I forgot to include that, my mistake. Negative 34 over 3. And we know that tangent, because that's what our problem gives us, is going to be negative 5 over 3. And that is going to equal the sine of theta. Okay guys, so this is our last part to the example problem. So here you see we're going to be looking for the cotangent of negative theta. Now, I know what you're thinking, or at least this is what you should be thinking, is that, hey, we're going to be using the even and odd identities right off the bat. And you would be correct, but remember, we're trying to find an identity that incorporates the use of the tangent of theta with the cotangent of theta, because we are looking for a problem that's going to have to utilize that, right? So you cannot go straight to using the even and odd identities. But what you can do is use the reciprocal identity, and here's how we're going to do that. So we're going to take the cotangent of negative theta, and that's going to be equal to 1 over the tangent of negative theta. Remember our reciprocal identities? And now we're going to get rid of this negative, on this side of the equation so that we can just get our normal old positive tan. Oh, don't know what that is. 1 over negative tangent of theta. So our equation now becomes that. And because it tells us that the value of the tangent of theta is negative 5 of 3, we can now say that the cotangent of negative theta is going to be equal to 1 over negative 5/3. Sorry, I didn't make that a pretty distinct one. And that is going to give us, you're going to have to do 1 times, when you multiply this, it's just going to be negative 1 times a negative, that's a positive, times 3 over 5, and that's going to equal 3/5. So ultimately, the cotangent of negative theta equals 3/5. And that's our last answer. All right, that's it, guys. Thank you so much for watching. Bye.